Hello, thank you very much for coming and thanks for having me along. Can everyone hear all right? Brilliant. So as you'll see, this panel session is looking to the future, solving strategic challenges and creating opportunities. It's about mathematical sciences as applied to the world at the cutting edge of human endeavour, driving discovery. On the train over here, I thought I'd read a bit of G.H. Hardy's Mathematician's Apology. I don't know if, I'm sure a lot of you are familiar with it. He has different views on applications. He says, the real mathematics of the real mathematicians is almost wholly useless, and it is not possible to justify the life of any genuine professional mathematician on the grounds of the utility of their work. He added about applications of the sort of things that we're going to be talking about, that practical applications, and you can almost hear the sigh in the parentheses, the bridges and steam engines and dynamos obtrude themselves on the dullest imagination. So we are here today doing something that Hardy would, of course, be appalled of. He would be appalled to know all the additional applications of mathematicians beyond dynamos and bridges that we're going to talk about, the cryptography, climate change, and AI. And he would also be saddened to know that, in my view, we do have a panel of genuine mathematicians here, despite the applications that we're going to talk about. And we're going to begin, I think, with probably one of the most important challenges facing the world and a place where mathematicians can make a big difference. We're going to begin with climate change, and Professor Emily Shuckburgh, she is a climate scientist and director of Cambridge Zero, the University of Cambridge's climate change initiative. She has worked with the British Antarctic Survey, the UK government, and the King, co-authoring a Ladybird book.
Thank you. So, the mathematics to help predict the future is, I think, one of the most powerful aspects of mathematics. And I don't think it's boring, I have to say. I think that our ability to use mathematics to help understand complex systems like the weather and climate is not only reveals the beauty of those systems, but also is incredibly powerful for helping us make incredibly important societal decisions. Over the last 100 years or so, our ability to be able to characterize the physics of the atmosphere and the oceans and the ice and how those connect together has enabled us to create predictions of the future that have had a huge impact on, maybe not as much of an impact as we would like, but a huge impact on societal decisions and policy-related decisions. It's enabled us to understand how, as we increase greenhouse gases, we will change our climate system. It's allowed us to understand how different parts of the climate system are coupled together. So right at the moment, we are experiencing a weather phenomenon called El Niño, which changes weather patterns around the world. And that El Niño phenomenon happens as a consequence of the coupling between the dynamics of the atmosphere and the ocean in interesting mathematical ways. We know that there is a severe danger that if we continue to increase greenhouse gases, we risk the Earth system passing tipping points, another incredibly powerful mathematical concept. And so we can understand the risk of the ocean circulation being in two different stable states, and the risk of that occurring, and the risk of the Amazon rainforest passing a tipping point that means it turns from a rainforest into a more savanna landscape, or the risk of the ice sheets covering Greenland and West Antarctica similarly passing a tipping point. What we're starting to do now is evolve our mathematical description from just being based on a description of the physics and chemistry of these systems to now including more data-driven approaches, integrating AI in particular into our forecasting systems. And that's unlocked even greater potential and power in our ability to understand and to predict those systems. So we're now using data-driven approaches, for example, to help predict the weather over the next few hours, to help design a more efficient operation of wind farms. We're using AI approaches to integrate different types of data sets, enable us to understand the risk to human populations around the world from extreme heat in terms of excess mortality, and then how to put in place measures to support that. And then finally, I think perhaps most powerfully, I have seen the role of mathematics as the glue that links together different disciplinary areas. So increasingly on the climate side of things, we're looking at climate-related problems and solutions from a systems perspective. There's a project that I'm involved in at the moment that's looking at how we might be able to manage our land differently in the UK for the benefit of climate and nature and the people who live and work in those landscapes. It involves a huge range of disciplinary expertise across the sciences, technologies, and social sciences, but it's mathematics that brings all those different disciplines together, and that, in many ways, I think, is the most powerful aspect of mathematics.
Thank you very much. I should have probably actually, basically my sole job was to explain the format, which I failed to do. Each of the panelists is going to give us a 3-minute pitch, and then we're going to have questions and among ourselves, and then we're going to open it out to you guys to maybe ask a few questions as well, which would be great, and then wrap up in about 50 minutes. But before we move on, one of the things that I find interesting about climate science and mathematics is how much do you need the maths to work in it? Or do you simply need to be aware there are a group of people who are familiar with this maths, who are doing the maths things, and then you can be a climate scientist and sort of just accept the maths people do the maths stuff?
So I have been amazed in many ways how across my career of working in climate science, in different ways, at different points, mathematics has come in. I spent some time, when I was at the British Antarctic Survey, I was particularly studying the ocean and the amount of carbon that gets taken up into the Southern Ocean. And critical to that is understanding the mixing processes in the Southern Ocean. And that requires you to understand the mathematics of the mixing processes. So you're hidden away in that particular challenge is mathematics. As we started to use more AI and machine learning, then I went back to some of the mathematics that I did as an undergraduate in terms of linear algebra, and it turns out that things that I never thought I was going to be going back and using again have been valuable. So I think that in many ways, the mathematics provides you with this incredible toolkit to be able to deploy in different ways across different problems. And at the same time gives you that sense of, the comment that I made about the glue linking together different disciplines, I think is also really valuable. Like we end up being able to be that connector between different disciplines that otherwise it's really quite difficult to integrate together. So.
Great. So our next speaker is Steve Brierley, who is Chief Executive of Riverlane, a quantum computing company. He advises the UK government, has worked in intelligence, and is a Senior Research Fellow at the University of Cambridge.
Thank you. So 100 years ago, Paul Dirac wrote this paper where he set out the equations of motion for electrons and atoms, quantum mechanics. So what we now refer to as the Dirac equation. And it has this wonderful line in the paper where he says, and thus a large part of physics and most of chemistry has been solved. And the only problem is to solve the equations. And over the past 100 years, we've been trying to solve these equations. We've been trying to make approximations to them so that they become solvable. And you have whole fields of computational chemistry, of solid-state physics, trying to approximate these equations, essentially throwing out some of the science to get to something solvable. And the premise of quantum computing is that a really neat way to solve these equations is to build a computer whose internal operations are the same as the equations themselves. So if you can build a computer that operates in the same way as these quantum mechanical equations, then perhaps for the first time we could solve Dirac's equations. And that would have profound impacts across industry and many of the huge societal challenges that we face. Imagine if you could design on a computer a pharmaceutical, a new medicine. You could watch as a protein moves to find new binding sites. You could try many thousands of ideas in hours instead of testing one over years in a laboratory. So in healthcare, this could have potentially huge benefits. We could solve some of the chemistry problems in designing new catalysts to address climate change, to reduce the energy consumption in industrial processes. 2% of the world's CO2 emissions are spent producing fertilizer. This is basically happens at room temperature in nature. Plants fix nitrogen with standard atmospheric pressure, yet the only way we know how to do it is the Haber-Bosch process, which uses a huge amount of energy. So I think this is a transformational potential technology, and the challenge, of course, now is to actually build a quantum computer. So that's extremely hard, and I'm going to get to what Riverlane does in a minute, and mathematics. The big challenge in quantum computing is that the qubits, the quantum bits, so the transistor equivalents, are extremely fragile. We're talking about an individual electron being controlled with exquisite control. And so the best quantum computers in the world today can perform about 100 operations before the errors in the system start to build up, and essentially you just get random noise from the computer. Now compare that with your computer that you have at home or in your pocket that can perform trillions of operations. So there's a really big gap between the quantum computers we have today and the quantum computers we need in order to solve Dirac's equation. Now the good news is that there's a technology which solves that, which is called quantum error correction. So quantum error correction works very similar to classical error correction in that you add additional quantum bits so that if any one of them fails, you can still recover. So that quantum error correction is similar to error correction. There are some subtle differences. For example, the first thing you learn about quantum mechanics is Schrödinger's cat. And so there's this cat that's in an alive and a dead state. But whatever you do, don't look in the box, right? Because otherwise it will collapse. So this is one of the challenges to actually implementing quantum error correction, because you can't observe the state of the quantum computer. And so the field has developed a whole bunch of really neat tricks to observe the effects of errors without observing the computational state of the computer. So that's just to say there are some really cool things in quantum error correction. And at Riverlane, we are solving this problem across the whole industry, so for many different quantum computing companies. And we employ a huge number of mathematicians. And that's because solving error correction means solving a very complex maths problem. Essentially, we get some data from the quantum computer, and then we have to infer the most likely error given this data. So we don't get to observe the effects directly. We're not allowed to look inside the box. We just see some hints about what's going on. And we have to solve this problem very quickly because it's right inside the clock cycle of the quantum computer. So we design dedicated chips to do this, and this is why we're based in Cambridge. So mathematics is really central to what we're building at Riverlane. And I think, just to echo this point of, it's really the mathematicians who are great at gluing together the engineers, so the people who know how to build chips, the physicists who understand how errors occur in quantum systems, the chemists and the material scientists who understand what are we going to use quantum computers for. And I see really mathematics as very central to that.
If we get a quantum computer that's sort of useful and does things, the barrier to doing that now, is that maths or is it engineering?
To building a quantum computer, you mean?
Just one. I mean, I know that there are quantum computers that exist, but ones that are usable and useful.
Yeah, so we need to scale up the system. So we've broadly understood, I think, the science challenges for the next 5 years. I mean, there are still challenges to continuing to scale this up. But over the past 2 decades, we've had enormous progress in the field of building individual qubits. And so the challenge is scaling up these systems and solving some of the systems engineering challenges.
Yeah. Thank you very much. We'll come back to all of this stuff in the sort of group discussion. But Professor Charlotte Watts, you are Chief Scientific Advisor and Director for Research and Evidence at the UK Foreign, Commonwealth and Development Office. And you are seconded from the London School of Hygiene and Tropical Medicine, where you are Professor of Social and Mathematical Epidemiology.
Great. Yeah. Okay, my pitch. So yeah, I am a mathematician by training. My PhD was in theoretical mathematics. So, I mean, your quote at the beginning about the beauty of theoretical mathematics, I mean, it probably took me 2.5 years to understand the question that then I could solve very quickly once I understood. And it was, I mean, I just to say that is such an important element. But actually, what I'm excited about, and I feel like I'm on the really dirty applied end of the spectrum of application, is how do we use mathematics and the tools that mathematics gives us, as well as wider scientific thinking, to shape and support the government to make decisions. I sit like in FCDO, I have counterparts in other departments as chief scientists. And what's interesting for me is how frequently I'm essentially relying either on mathematics or the tools that we get from mathematics. And so just to give you a flavor of how it comes up in my life, for example, a whole host of examples I could give you about how we are needing to respond very quickly to international emergencies. We could talk about the Ebola outbreak. My first big one was Zika when I first came into my department. COVID clearly was an example where we were using complex epidemiological modeling to think and understand about how disease transmission is spreading and our interest is in what does that mean about what we do. In other cases, we are combining different sorts of data. So, for example, Cyclone Idai is one that I remember well. It happened in 2019, hit Zimbabwe. You had extreme floods, heavy rainfall. So then we were linking up with the sort of Met Office, universities to say, okay, let's understand what are the projections. Are we going to continue to have heavy rain? But also we needed to combine that with data of where are people moving to, right? Where are populations that are vulnerable? What was our understanding about levels of vulnerability? We were drawing on both shallow water and deep water fluid mechanics analyses that we were commissioning from Reading and Bristol to say, actually, what are the downstream effects? Are we going to end up having a dam breaking, and we have to prepare for that? And what we're doing there is using different mathematical elements, but what we need to do is combine it really quickly with on-the-ground data and then get that data into a usable format that we can then share with the humanitarian community as well as our partners on the ground. And so for me, the big issue is, can we apply this well? Do we understand the opportunity of maths? But also then how do we get it into decision-making, both of the things that we might be doing as a government, but also to that wider international community. And that example of one of, when you're saying about combining or kind of reflecting on how do you combine data at pace, the mathematics and the tools around doing that are phenomenally of interest to us because we end up dealing with lots of emergencies. And sometimes my interest is, actually, are we too slow? And some of the tools that you might be thinking about in other applications, could we use them to be able to move very quickly and shape decisions when we're really sort of kind of we have to make decisions in minutes or hours or days, which is sometimes the kind of dynamic that we're talking about. Another example I could give you is really boring mathematics and really simple sort of regression type analysis. You'd all be bored stiff. I could give it to probably an A-level student as a little project. But actually, for me, what's important isn't what is the sophistication of the mathematics, but what is the mathematics that helps us inform our thinking. So, for example, we had the midpoint recently at the UN of the Sustainable Development Goals, global ambition to improve the world across many areas, including in health, climate, and so on. The common narrative is the world is behind, but actually the data was really variable. And when you start looking at that data, a lot of it's correlated. And there's differences by country. You've got some countries that are following a trend that you might predict by the GDP level of that country. Others are outliers. Some are doing better than we might expect. That's really interesting. What's driving that, right? So, we did a whole lot of analysis just internally using our internal statisticians and experts in different sectors to go, actually, what does that mean for the UK about what we want to lobby for in the UN agenda? And actually, science and data and analysis was part of what we were saying we need to use to accelerate that more strategic thinking and more targeted investment. So for me, it's not how sexy is the science or the mathematics, it's actually getting it to where it can form a strategy. And then the last example I want to give you is some of the things that we've been doing to support partner countries in their journeys to try and achieve net zero or to move to cleaner transmission. So some of the research that we've been supporting, for example, is developing tools that ministries, so for example, South Africa government, can draw upon, or other countries can draw upon to think about how do you move from fossil fuels to clean energy without the lights going out. That's a non-trivial problem. It requires a lot of data, a lot of complexity in the sort of investments you might need to support that. And some of the opportunities we have in the UK of being strong in these areas is to say not only what are the tools we can use domestically, but also how we can share some of those tools for other countries.
And when you're within Whitehall, I mean, people like Kate Bingham have been very, very scathing about the scientific understanding she finds there, and people like Dominic Cummings have been even more scathing about the scientific understanding. Is that sort of fair? Do you feel you're there on your own as a person with the sort of mystical ability to use Microsoft Excel?
I think that's a pretty harsh representation. And what's interesting for me, so one of my jobs as chief scientist is being head of a range of technical professions. So we have lots of economists. We have, if I just look at my own department, we have lots of economists. We have lots of statisticians. I have health experts. I have climate scientists. So actually, there is a breadth of deep technical expertise that we can draw on. So it's not as grim as the picture that you're saying, but we do need more. And we do need those people both in sort of broad policy positions as well as in specialized roles. So one of the things I'm very interested in is how do we first get more mathematicians, scientists in through our recruitment processes into government, but also how do we support careers that both either support specializations or alternative get those into the sort of wider ecosystem of the government, so the people who understand about numbers, about analysis, around logic and so on. And actually, when I look across Whitehall, a number of perm secretaries do have mathematics as a background. I was quite surprised once I started digging that it's maybe not as negative as you think. And I mean, sort of last point, I just in COVID, the extent to which people, even who initially hadn't thought about science, started to think about science, started trying to understand the data. There's quite a big opportunity building on that of actually how do we kind of continue to highlight the applications of maths, of the tools from maths in the civil service and inspire others to get more involved in the sector.
And how do you, as a scientific advisor, how do you get chosen, and how do you get inducted? Does someone sit you down and say, this is what you need to do?
It's a baptism of fire, actually, if I'm honest. But yeah, I mean, like any recruitment for anything, there is a competitive process. Chief scientists have a fixed term that they're in. All the chief scientists have breakfast every week, so we're a very tight network. So there's a lot of learning across the different departments, but also sharing information because ministers rotate, so we all share intelligence about what's happening next. But also you tend to have conversations with your predecessor. So Chris Whitty was my predecessor, and we went and had some sort of conversations beforehand just to kind of understand what are the hot topics. I mean, the other thing that is really you learn over time and by watching other civil servants is just how do you communicate quite complex ideas in an accessible format. And the skill is not to dumb it down, right? It is to say, how do you capture the key essence of what is the issue that the minister has to understand in a simple and accessible way. And sometimes what you can help you use analogies or other things, but that is actually more the skill set that as a scientist you aren't trained on, but actually is really important if you're going to support a minister who might not come from a technical background to really sort of understand, look, this is the issue that you need to understand and what that means. And we've had conversations about El Nino, La Nina, tipping points, for example, in the last month with ministers, some quite big concepts that it's really important that they understand.
Yeah. Thank you very much. And finally, we have from the sort of, I guess, the most private sector, obviously with Riverlane, with Piers Stobbs, who is the Vice President of Science at Deliveroo. Before that, you worked building algorithmic systems at Kazoo and Money Supermarket, and you are also a member of the Royal Statistical Society's AI and Data Science Committee.
Great. It's really lovely to be. I have to say, I just comment, the idea of a chief scientist's breakfast does sound rather entertaining. I would quite enjoy that, I think. I also just commenting, Charlotte, like if you're on the dirtier and applied end, I'm not quite sure where that puts me. So yeah, I'm definitely representing, I guess, a more general kind of industrial view on kind of mathematical sciences, in particular data science. I've been fortunate to work in data science for a very long time, grey hairs, in fact, long enough so that it really wasn't called data science when I started. I think one key about the underpinning of the education that got me here was this. I've been able to leverage it into a lot of different interesting roles across a variety of geographies and a variety of industries. I spent some time in hedge funds. I worked at Dunnhumby Tesco, so groceries. Money Supermarket was all about helping people save money. Kazoo selling things online, and now Deliveroo delivering food. So a wide variety of problems, and I really think, well, definitely not quite as awe-inspiring and long-term saving the planet as climate change. There are definitely societal goods and improvements to life in general that I think the underpinning of these approaches really do drive. I thought I'd maybe just touch on maybe 3 quick examples, actually, of the types of problems that the sort of mathematical sciences and data sciences education and background can really work on in industry. And maybe first starting with Deliveroo. I mean, in the spirit of audience participation, has anyone had a Deliveroo delivery? I'm guessing a few. Oh, that's pretty good, you know. Probably not the most representative sample, but hey, we've got a few. I think, so the interesting sort of maths problem with delivering food to customers is, well, we at any point in time, we have hundreds of thousands of orders around the world. You know, we work in a bunch of different places, and we have hundreds of thousands of riders who we don't control at all. They're just out there, self-employed. And we have to decide, well, which order should we give to which rider? And intrinsically, it sounds very straightforward. You just give it to the one who's closest. And you sort of think, as soon as you start extrapolating from there, you realize actually it's not quite that simple. And I think what I think is intriguing about the problem is it incorporates some hardcore computer science, because we're talking real scale. Again, if you think about hundreds of thousands of combinations that are going on, we've got to do it at every 30 seconds. Being able to actually compute that in an efficient way is a real challenge, and certainly something that maths underpins the underlying software and algorithms about how you do that. But then there's the sort of slightly more mathematical bent around operations research, which is, well, given a set of orders and riders that you've kind of aligned, how do you know whether that's better than another set of orders and riders you've aligned? You've got to come up with some mechanism that allows you to judge between all these different plans. And that's a classic operations research problem. You have to come up with some sort of cost function, some sort of evaluation, which for us takes into account the efficiency of the network and things like service. You know, you could very easily think about how we could just give all the orders to one rider. It'd be brilliant. They'd be so efficient, but everything would be late. And so again, you've got these trade-offs that you have to make, and you define that mathematically into a function, and you try and minimize that function in an efficient way. So a really elegant solution, and we've used that to drive basically the success of the business over the last 5 years. So great fun. Another interesting example maybe from Kazoo, so that's e-commerce. Again, I'm tempting fate here, but did anyone buy a car from Kazoo? Yeah. Oh, one. Fantastic. Happy with that. Oh, another. Yeah, so very happy about that. You know, I'm proud of what we did in Kazoo. You know, I joined when we were only 20-odd people, and I left when we were 3,500, and we sold an awful lot of cars. We're up to $1 billion in revenue by the end. Interesting mathematical challenges there. There were some fun geospatial ones around where should you actually position sort of pickup positions around the country, thinking about how you sort of think about, you know, that as a sort of mathematical problem. But probably the most obvious one is price elasticity. So actually, what should we price the cars at? So in this case, there's a market price, so we kind of know roughly what everyone's everything costs, but it becomes this trade-off between profit and throughput. So again, it's about framing this problem, and there we use some interesting machine learning equations or approaches to actually to derive some price elasticity models actually at the individual car level. So again, it becomes this optimization problem which says, well, if we reduce the price of this, it'll probably sell quicker, so our throughput will be higher. But if we increase the price, maybe the profits are worth it. So again, it's about formulating this optimization problem in a way that you're driving the outcome you want. So again, hardcore, proper maths, machine learning, optimization. Just finished then with grocery. I think this will be a better one. So who's shopped at Tesco? Oh, look at that. Nice one. What I love about the grocery space is we've all done it. We can put yourself in the customer's shoes. And what I think is intriguing there is how much you can derive, how much insight you can derive purely from behavioral data, purely from the patterns about how people shop. So if I'm, for instance, the manager of the grocery, of the cereals aisle, I have to think about what's called substitutes and complements. Like, I have to think about how much of the shelf space I should put cornflakes versus Cocoa Pops. And so you think, well, you could go through the 40-odd thousand grocery items in a store and manually think about, is this a substitute for this? Is this a complement for this? And, that's certainly an approach. But what's lovely is if you take the insight that an individual generally only buys complements in the same basket at the same time, not all the time, but in general, and probably only buys substitutes in separate baskets, because again, why would you need both at the same time? That allows you to develop these pairwise relationships between products purely from that underlying data, purely by saying how often do these things appear together and how often do these things appear apart with the same customer. And that allows you, again, this really interesting insight about, well, maybe I should have mint sauce and lamb next to each other. Obviously, that's an obvious one, but it's those types of sort of underlying data analysis that led to, the beer and nappies anecdote from Target in the States. Anyway, just a couple of ideas, a couple of sort of instances of where, what we do, what we're able to do, the skills we have, solve real world problems, which is, I love, it's great fun.
And with someone like Tesco, so it's obvious Tesco starts selling groceries and then comes to realise that mathematicians have their uses. With something like Deliveroo, did they set it up and then think, oh, hang on, we've got to solve the travelling salesman problem, we should find ourselves some mathematicians? Or was it from the beginning, did they realise that this is effectively a maths company with some riders?
Yeah, it's a great question. And I think I was fortunate in both Kazoo and at Deliveroo that actually there was that underlying understanding from the CEO from the start that actually, yeah, we're going to need some hardcore science involved here. I do think that that's an interesting question. And I think parallel to what Charlotte was saying, I think the more we can get technical leadership involved at an early stage in companies, the more there's that realization about what this type of approach can bring and how it can help solve problems.
And to what extent is the problem, the problem that Deliveroo is solving, I don't hope this isn't insulting, it feels to me like it's similar to what a lot of companies are doing. Mm-hmm. Is there a semi-off-the-shelf thing that you do, and then you tweak it? It's
an interesting question. I was fortunate to try and explain this to a bunch of investors around why Deliveroo is really different. But I think the interesting one is you think it's the same as, say, ride sharing, Uber or anything. But what's really interesting is, so at Deliveroo, we have to build a model for every step of the way because the food doesn't walk to the door, if that makes sense. So we have a model for every restaurant about how long a particular meal is going to take. We have a model for every route, obviously. We have a model for every address about how long we think that a particular rider is going to take to actually get there. Because again, people expect the food to come to the door. So it is actually quite a lot more complex than, point A to point B, which is typically what the sort of taxi type service does.
Yeah. Fabulous. Thank you very much, everyone. We are going to have a discussion. I've actually read more closely through my speaker brief, and I don't think we are interested in your opinions. Someone can sort of... Oh, someone's waving vigorously. Is that correct at the back? Yes? Yes, we're not. Yes. Okay. So if someone can come and tell me otherwise. Oh, no, there is a microphone there. So, yes, we will be. But I will ask a few questions and reverse that entire ferret. One question... For all of you, to what extent does it matter that this mathematics is so far removed from what most people are ever going to understand? And I don't think that's patronizing. I think that works. I mean, quantum mechanics, I mean, frankly, you guys could be making up all of this stuff. It could be some sort of, just some art project that's gone wrong and you're convincing the world that we can talk about these particles being all these sorts of places. Climate change is something where it's absolutely affecting everyone, all of us, but the plumbing is this mathematics that, we're not going to understand and have to trust. And then I guess that the proof in your mathematics is my food's arrived. So that's better. But then equally, you've got to explain this to people who have no maths background at all. So maybe starting with you, Emily, does this matter?
I think it really, really does matter that people understand some of the mathematics, because especially in something like climate science, we trust in the outputs of climate modelling in particular is really important. We're essentially, as a society, are asking people to make substantial changes to their lives. We're effectively saying we need to change the entire global economy. That's not a small thing to do, and you want to make sure that you trust the evidence that decision is being made on. And so since that modelling is in climate science and in many other areas that we've been talking about, absolutely at the heart of that decision-making process, then ensuring that we have ways of being able to explain, it comes down to something that Charlotte was talking about in terms of explaining to ministers, but it's not just explaining to ministers, it's explaining to society at large the basis on which we're making those decisions and giving them, I think Charlotte put it very well, not necessarily the finer mathematical details that they might not have the background in order to be able to understand, but giving them a sense of some of the critical elements of how that modelling process has occurred, giving them a sense that modelling process is robust, is really essential in terms of helping to build trust and ensuring that entire process is transparent and that there is an ability for those who do have the skill set to be able to interrogate it is also critically important. So I think there is something about ensuring some involvement of wider society in that decision-making process that is essential if you're going to be trying to actually enact radical change.
But how do you do that, and at what point do you just say, well, you've got to take this on trust, we've got our differential equations or whatever?
Well, I think it's in multiple different ways, and I think there's not a simple answer to that, of course. But it really is about engagement at all sorts of different levels. I think some of the things that many people in this room will have been involved in, even at a small scale, in terms of involving school children in different projects that gives them some insight into how mathematics is used in the real world. Building up from that through to ensuring that the data sets that we're using to help generate some of these new AI-based methods, along with some of the methodologies associated with those, are open to external scrutiny and transparency. There's just multiple different ways in which it's important to do that, and there's not one solution, but it's about a package of different measures. And of course, one of the most important aspects that comes across all of these, and again, Charlotte touched on it somewhat, is the fact that through the output of many of these different societally relevant evidence bases, is that there's scientific uncertainty associated with them, and providing a wider population with the tools to be able to understand how to interpret scientific uncertainty and describing that scientific uncertainty in ways that people can usefully build into their own decision-making processes is also critically important.
What about quantum mechanics? Do we just have to accept we're not going to understand how a quantum computer works?
Yeah, I was trying to think. I mean, maybe Moore's law is a good example here, right? So current technology does look like magic. I would argue that your laptop and my phone looks like magic. And that's, I think the lesson from Moore's law is that if you have this compounding effect of year-on-year improvements, essentially getting twice as good every 12 to 18 months, over the period of a decade, what the current abilities just look absolutely astonishing. I think the key is demonstrating concrete proof points, so showing things that really work. And I think quantum is maybe one of those areas where it perhaps has been overhyped, certainly in the past few years. And I think that's largely been people wanting things to happen more quickly than they really can. Right? This is a hard problem to solve, and we need a decade to solve it. So I think then it becomes incumbent on the people in the ecosystem to explain, okay, like this is hard, but here's where we were 2 years ago, and here's where we were 5 years ago, and this is what progress looks like. Because I do believe that quantum is already exciting, even if you only say things that are true.
Yeah. Well, very quickly, because we do want to get to questions. Charlotte, does it matter? Are people disconnected, and is that inevitable, and does it matter?
You talked about it. I think to get people excited about mathematics, school children excited about mathematics, starting to show the applications, or where is their hidden maths in the things they care about or excited about, is a really important part of the change that you were talking about in our education system. And having flexibility, so if you're not very good at one aspect of mathematics, it doesn't mean you can't do maths. You can pivot on and do something else, because the breadth now, when we think about the skills of mathematics, from coding to different equations, so sort of more theoretical work is so broad. I wanted to pick up a bit more on though this issue of how do we deal with the importance of, and for me it's how do I ensure that a minister or my seniors understand and can think about issues when it's very complex. And for me it's that, and it was just a really live issue with COVID, for example. So I was on Sage, you've got Julia coming later and speaking, and there we had to be really, in a way, the role of people like me is to try and be that interface and understand what is the debate in this area, what is the scientific or technical view or the modelling view. So if you look at the modelling for COVID, you didn't have one model. You had multiple models. You had SPI-M then looking at that spectrum and then saying, actually, where is their agreement and where is their disagreement? And then when I would be taking that back to my department and saying, this is where we feel really confident. This is where there's much more less confidence. So that ability to say, where do we trust where we are, and where is it where actually there are different views, is a really important part of how we think about understanding and interpreting mathematics or using mathematics. And I think it's the same with the general population. We shouldn't say, in a way with climate change, it's so fundamentally clear, we should just be very fundamentally clear. But having, for example, the Learned Society, the Royal Society came out quite early on and said, the science is unequivocal, we have to take this seriously. Those sorts of voices are really important, because the general population aren't going to understand the complexity of the modelling. In other cases, we have to invest so we get a better handling, I think, of the uncertainty or the risk. So clearly AI and the applications of AI are a really important area where we need to be thinking and talking about the opportunity, but also investing in understanding what are the underlying sources of bias, what are the risks, what might be the ethical, there are different perspectives you need to pull together. I don't think, I think it's just how do we have that nuance in any conversation about applications of science, data, AI, be it with ministers, be it with the general population.
And Piers, presumably you care that you've got mathematicians, but when I order a post-pub kebab.
So there's some lovely comments here, and I think how we frame and how we communicate is so critical. Maybe I just want to take a slightly different slant in that a lot of what I do is very applied, and I don't have a PhD, and I think there can be, on the practitioner side, sometimes a reluctance to delve into adjacencies, to delve into things that maybe they haven't really sort of spent or don't know inside out. There's the joys of probably us all, like we really like to know stuff. And so I do think some of the most exciting work I've done is where I've kind of edged into these areas that I am kind of less familiar with, but my underlying basic science allows me to pick up enough. Now, some would say enough to be dangerous, but enough to, to explore how that approach might be applied elsewhere. So I think there's a barrier in general in the sort of communications, but sometimes there's a barrier like internally within our community around what problems people approach. And I think there's certainly something there we can try and evangelize a bit more.
We do have time for a couple of questions from the floor if people have them, and I think there's a mic coming. So if we start with the gentleman who put his hand up first at the SU, yes, at the back, and then I'll work forwards and hopefully.
Thank you. Ed Rochette, among other things, chair of the Alliance for Data Science Professionals. Building on Sir Adrian's initial thoughts, I was wondering what the panel felt were the real opportunities in terms of careers for solving strategic challenges and creating opportunities. So how would you shape the curriculum at A-level degree or even beyond that? Do we need to embrace degree apprentices, mid-career changes and so on? How do we create the community that's going to make that happen?
Okay, should we start, Piers, and go this way?
Yeah, I mean, I think it's funny having sort of somewhat randomly ended up doing what I do when there wasn't a career, there wasn't really a sort of an approach to any of this. So I have a really strong affinity for getting the groundings in a core STEM subject and really sort of understanding how to learn, so to speak, because I think what the data science approaches evolve so rapidly, so quickly that sometimes focusing on a very applied curriculum is just going to go out of date almost immediately. And while it's very beneficial in the very short term, doesn't actually help solve people or help people in the longer term. So I would be still very supportive of kind of funneling people into those core subjects with then applied sort of approaches on the top of that. I definitely think there's a whole slew, and I'm sure I'm not it's not rocket science, but about how we talk about maths and how we teach maths, and framing it in ways of real world problems that actually can be useful in real life, and that can be at primary school, frankly, but all the way through degree programs. It's not just a distribution you have to learn. It's actually going to help you solve this problem for your mortgage or whatever. So I think there's definitely a piece around education on how we frame those courses.
Okay, other panelists, but rapidly, and I think we'll try to get through a few more.
Yeah, I mean, I sort of agree with your points. I think, clearly you have to teach the core skills and analytic approaches, but bringing in examples so it keeps its relevance, it keeps being exciting, it keeps being fun, I think is the bit that we need to invest in as well.
Yeah, so I have two daughters who are 8 and 10, and they hate mathematics, which pains me deeply. And they hate it because they equate it with arithmetic and having to learn their times table, which they think, and I have to somewhat agree with them, is just incredibly boring. And what they don't get taught at school is the beauty of mathematics, that kind of pleasure of that you gain from solving some complex problem. And as we've been talking about on the panel, the central relevance of mathematics to so many real-world problems. I think it frustrates me deeply that, and it's not just my daughters, of course, it's children throughout primary school are just not getting the excitement of mathematics, and I think that is something that I would dearly love to change.
I'm going to take two more questions, and then we can answer whichever one you want. So I'm just going to work from the back. The lady there, and then the gentleman, I think, over there.
Hello, thank you. My name's Rachel. I work at MEI on the Advanced Maths Support Programme, and so I taught maths for over 20 years. First thing to say is, hang in there, Emily. My daughter hated maths until she was 16, and then she came home and she said, Mum, I've chosen A-level maths. So that's brilliant. So my question is a really cheeky one, but I hope you know where I'm coming from, which is perhaps to Piers and others on the panel. Would you consider changing your job title. So what I'm thinking of is, I'm thinking of the public perception and young people's perception, and it's things you've mentioned. Would you be the vice president of science and mathematics or something like that, so that young people can see that mathematics is involved in these really interesting areas?
Absolutely. It's a tricky one, isn't it? I think fundamentally what we're trying to get across is that if you do a maths degree, this is what I'm passionate about, you can do any job. I personally think that, and I think that is just not what comes across, I think, to undergrads or even A-level students or students these days. Just the wealth of opportunities that it brings is I think the problem that we have at hand, and I guess more events like this. But I'm open to any suggestions around how we do that.
Great. I think we'll stop it there. And sorry, I've realised. Can we have the gentleman there? Is it gentleman? I can't quite see. Apologies if you're a lady. Sorry. Yes.
Sorry to the gentleman who didn't get the question. I was wondering if you kind of notice how, as the society is getting more and more technical and we need mathematics and science literacy, we've also seen a rise in conspiracy theory and this kind of general divide between people who seem to kind of have ideas that we didn't see so much like 20 years ago about the Earth being flat and things like that. Do you think there's a link between the two? And what kind of ideas do you have to kind of help reverse this divide that we've seen in society between people who are kind of very much lacking in terms of science literacy and people who are kind of like you at the forefront of scientific research?
So very quick answers. I'll come to Steve if we haven't come to him, but I think possibly Emily's also got quite strong thoughts about conspiracy theories.
Yeah, quantum definitely comes up in the conspiracy theories too. And that's possibly partly our fault, since we do things like teleportation and so on, so which we can't actually do. I think, it's really on us to be in the middle ground, right? And to be as loud as some of the conspiracy theorists in terms of communicating well about the real underlying things that are happening, and that they are exciting and important and engaging with people. I suspect it's where people who are not engaged that then drift away into other areas. I mean, I'm not an expert, but I think it's really for us to land the central messages and to, through events like this, talk about like what really is happening and what's exciting and why it's exciting, and then inspire people to be involved in the core sciences.
Finally, Emily.
I think it comes back to this trust issue that I was talking about earlier. So it is not the case, actually, that the most, that you stop people going down the route of conspiracy theories by just telling them more information or that people with more knowledge or degree subjects in science are less prone to conspiracy theories. It's more down to people's worldviews and political viewpoints and so forth. Certainly that's true in the climate area, where there's quite a lot of conspiracy theories over the years and misinformation. Certainly where we've made progress on this has been through exactly the measures that we've described earlier about openness and transparency and engaging people as much as possible in the underlying science and the development of that science. So the project that I was describing, where we're looking at how to change land management practices, right from the start, we've been involving all the different stakeholder communities in those landscapes in the design of the science itself, so that they feel that they've been part of the development of the projects and then the development of the recommendations that are coming out of those projects.
Very quickly, Charlotte.
Yeah, I mean, I just want, if you think about the echo chambers that we're now seeing people in, there's also just this fundamental question of what are the underlying algorithms behind that, right? So that, some of the issues where we're seeing that increased polarization is because the ways people are accessing information and the sort of systems that are directing to what do they look at next are not exposing to alternative views. So I just think there's a sort of tech view on this as well that we should be thinking about. That concerns me, and we need to think about. And then lastly, just let's really have less on the education one. Having a dyslexic son who could never learn any tables at all, so was in the bottom set. Just looking at primary school and that rote learning, it's so redundant. and it just is such a bad start to selling mathematics as an exciting area.
Thank you very much, everything. I've done the appalling thing as the chair, which I've kept you 4 minutes and 7 seconds away from your coffees. But I have good news, which is I've actually added 6 minutes because we're coming back at 12 rather than 12, because the Science Minister has had an unexpectedly busy week and is pushing our schedule while she answers some questions. So thank you very much, and thank you to the panelists.